In this videotape, we will study the polar coordinate system. Now, you're all familiar with the rectangular coordinate system, also known as the Cartesian coordinate system. In which each point in the plane is associated with an ordered pair of real numbers which measure the distance of the point from two mutually perpendicular lines known as axes. The horizontal line is known as the x-axis, the vertical line, the y-axis. They intersect at the origin. If you can imagine a man standing at the origin, and he is given a pair of coordinates to send him to some point in the plane, you could think of the pair of coordinates as an address of the point that he's going to. So he wants to go over here. The x-coordinate he looks at first, and if the x-coordinate is positive, he moves to the right, the designated number of units. If the x-coordinate is negative, he moves to the left, the amount of units written. When he gets there, he then looks at the y-coordinate. If y is positive, he moves up that number of units, and if y is negative, he moves down. For example, this might be, if he wanted to get to the point, say, 3, 2, that's what's written on the sheet, he would move to the right 1, 2, 3 units. And then from that point, he would move up 1, 2 units. And here we have the point 3, 2. Okay, now, you're familiar with this coordinate system. However, it is not the only coordinate system that is possible. Another coordinate system which we use is the polar coordinate system. Here, once again, we have that man. He's standing now at the origin. And let's say we want to send him to some point in the plane. Well, he's given a pair of coordinates, okay, which is the address of the point he's going to. And the coordinates are written in the form r, comma, theta. And a slightly different set of rules applies. He looks at the second coordinate, the theta, and he says, well, if theta is positive, he rotates himself through that angle in a counterclockwise fashion. If theta is negative, okay, he rotates through the angle in a clockwise fashion. If r is positive, he moves forward. And if r is negative, he moves backward. In other words, instead of having the choice of moving to the left, right, up, and down, we're going to send a man to a point in the plane by having him rotate himself through an angle theta and then to walk, okay, either you can rotate either clockwise or counterclockwise, and then to walk either forward or backward along that ray. So over here, he would have rotated himself through an angle theta and then walked out r units along that ray. You might think of the rectangular coordinate system as, say, suitable to direct somebody in the city, where you have the buildings and you have the blocks. You want to go over 3 blocks to the right and then up, go 2 blocks north. Whereas if you were in the country, it might be an easier way to get to a point by simply turning yourself to an appropriate angle and then walking forward. This might not be suitable in the city because you'd be walking through buildings. All right, now let's look at a typical point. By the way, I said the man was still standing at the origin. In the polar coordinate system, we usually call this point the pole. And instead of the x-axis, we call this the polar axis. And the man is standing at the pole. If you can imagine, his nose is facing out along the polar axis. That's the direction he's facing in. He is now going to be directed to a point in the plane. If theta is positive, he will rotate himself in a counterclockwise fashion, whatever number of degrees, say, theta is. If theta is negative, he will rotate himself in a clockwise fashion. If r is positive, he will then walk forward. If r is negative, he will walk backwards. For example, Let's say he gets the point 2, 30 degrees on his sheet of paper, and he wants to walk there. He is standing here, remember, facing out. The direction he is facing in is along the polar axis. 30 degrees tells him to rotate himself 30 degrees. Say this is a 30-degree angle. And then to walk forward 2 units. So this is the point 2, 30 degrees, r, theta. He was standing here, facing out, turns himself 30 degrees in a counterclockwise fashion because theta was positive, and since r was positive, he walks forward 2 units. What about the point 2, minus 30 degrees? Well, that would be over here. Minus 30 degrees would tell the man to turn himself 30 degrees, but this time in a clockwise fashion, and then to walk out 2 units. So this would be the point 2 minus 30 degrees. Okay, what about the point minus 2 minus 30 degrees? Well, minus 30 degrees, he would therefore he would turn himself in a clockwise fashion 30 degrees. He'd be facing now, his nose is facing along this way, except instead of walking forward 2 units, he would walk backwards 2 units on the extension of this ray. So we would get 1, 2, and we have here the point minus 2, minus 30 degrees. That is, he turned himself 30 degrees in the clockwise fashion. He rotated himself through the angle minus 30 degrees. That's 30 degrees, but clockwise. He is now still standing at the pole. He is now, instead of facing, though, out along the polar axis, he's facing out along the ray minus 30 degrees. Theta equals minus 30 degrees, and he now walks backwards 2 units. And similarly, we could have him walk along the extension of the 30-degree ray and get to the point minus 2, 30 degrees. That is, he would rotate himself 30 degrees in a counterclockwise fashion. He is now standing here but facing in this direction, then walk backwards 2 units. All right, now you might have noticed something here. Instead of, let's say you wanted to get to this point, minus 2, minus 30 degrees. One way of getting there is, as we've described, to rotate clockwise 30 degrees and to walk backwards 2 units. But there are other ways to get here. What about walking forward 2 units after rotating yourself in a counterclockwise fashion 150 degrees? In other words, here, from here to here is 30, and another 120 degrees to get to 150 degrees. Now you're standing here facing along this ray, and you walk out 2 units. Okay. Another way of looking at it is, if you're here, as this is minus 30 degrees, this is 180 degrees added to minus 30, or 150 degrees. 150 degrees, you're now standing here, facing out in this direction. You walk forward 2 units. Okay, so we see that there's more than one way to get to a point in the plane with the polar coordinate system. Now, this did not happen in the rectangular coordinate system. Going back over here, if I wanted to send a man to this point, there's only one way to do it. Okay, he has to move to the right 3 units and then up 2 units. It's the only way to do it. There is one and only one pair of coordinates associated with this point. We have what we call a one-to-one correspondence between the points in the plane and these ordered pairs of real numbers. Every point is associated with one and only one ordered pair of real numbers, and an ordered pair of real numbers directs you to one and only one point in the plane. Now, in the polar coordinate system, we lose this idea of a one-to-one correspondence. There is more than one way to get to a particular point in the plane. A pair, for example, a point here, we see can have more than one pair of coordinates associated with it. In fact, we will learn that there's really infinitely many representations, okay, for any particular point in the plane. Okay, the infinitely many idea, well, let's be silly about this. Let's say we want to send a man to this point. Well, we could tell him to turn himself 30 degrees and walk forward 2 units. However, what about telling him to turn himself 390 degrees and then walk forward 2 units? In other words, first spin yourself around, all the way around in a circle, that's 360 degrees, and then walk forward 2 units, and then go another 30 degrees, and then walk forward 2 units. So, go all the way around in a circle, and then another 30 degrees, that's 360 and 30, 390, and then walk forward 2 units. Or, let's say we're really nasty. We could have this poor guy spinning around for quite some time. Let's say 750 degrees. That is, go around the circle once for 360, around again for 720, and then an additional 30, and then walk forward. The man will be dizzy, but he'll get to the same point. Okay, so you can see that we do not have one-to-one correspondence here between the points in the plane and the ordered pairs of real numbers. By the way, if you want to write this as a pair of real numbers, instead of 2, 30 degrees, we know we can write this as 2 pi over 6 radians. Okay, we can write an angle 30 degrees is equivalent to an angle of pi over 6 radians. A lot of the work we do in polar coordinates is dependent upon the work that we've done in trigonometry. So if you're having difficulty with anything, okay, that we do that requires trig, I would suggest you go back and look over the videotapes on trigonometry. Now let's go back to the rectangular coordinate system, and let's look at the simplest equations that we came across. In rectangular coordinates, okay, in the rectangular coordinate system, typical coordinate was x comma y. The 2 simplest equations that we would come across would be, say, x equals some constant or y equals some constant. These represented straight lines. X equals a constant represented a vertical line, and y equals a constant, a typical horizontal line. For example, we could have x equals 2. That represented vertical line. It consisted of all those points that had their x-coordinate equal to 2. They would be located vertical line like so, 2 units to the right of the y-axis. For example, we would find the point 2, 0, 2, 1, 2, 2, 2, 3, 2, minus 1, 2, minus 2, and so on. So x equals 2 is the equation of a vertical line. And we might have also, we could have had y equals, say, minus 1. Y equals a constant is the equation of a horizontal line. In this case, y equals minus 1. It goes through the point 0, minus 1. It's a horizontal line. It's parallel to the x-axis, and it's 1 unit beneath it. So this is x equals 2. This is y equals minus 1. Every point on this line has a y-coordinate equal to minus 1. For example, 0, minus 1, 1, minus 1, 2, minus 1, minus 1, minus 1, and so on. So these are the simplest equations that we could simplest equations in the rectangular coordinate system that we might want to sketch. Similarly, the equations that we get by setting each of the coordinates equal to a constant value, okay, are equations we would like to sketch in the polar coordinate system. What are the possibilities? R equal to a constant or theta equals a constant. For example, R might be equal to 3 or theta could be equal to, well, you could use any number. For example, pi over 6 represents an angle. Any real number can be thought to represent an angle in radian measure, but just for what we're doing now, we could even use, say, 30 degrees. Where are all those points that have, in the polar coordinate system, that have r equal to 3? Well, for example, you could have a point, you could have 0 degrees 3 units. Would be here. We could have 45 degrees 3 units. So here's the 45-degree ray, go out 1, 2, 3 units. 90 degrees 3 units. 135 degrees, 3 units. 180 degrees. Remember, you're standing here, you're facing now out along this ray. It's 180 degrees, and you walk out 1, 2, 3 units, and so on. 270 degrees, 3 units. These points all fall on the circumference of a circle, okay, that has center at the origin or at the pole and radius 3. Okay, so the most basic curve that we could have in the polar coordinate system, r equal to some constant, represents a circle centered at the pole with radius equal to the absolute value of what's over here. I say the absolute value because, for example, r equals -3 would be the same circle. That would just mean, for example, at 0 degrees, you walk backwards 3 units. At 90 degrees, you'd walk backwards 3 units. At 180 degrees, you would walk backwards 3 units. So you would generate the same circle. Okay, so we have a circle centered at the origin, radius equal to the absolute value of whatever the constant is. Okay, the other basic equation in the polar coordinate system would be theta equal to some constant. For example, theta equals 30 degrees. Where are all those points that have theta equal to 30 degrees? Well, they're located along the ray and its extension, 30 degrees. For example, 30 degrees, 1 unit would be here. 30 degrees, 2 units. 30 degrees, 3 units. 30 degrees, 4 units. 30 degrees, 0 units. Okay, 30 degrees, and if r is -1, you'd walk backwards. If r is -2, if r is -3. So we would have a straight line. So theta equals a constant. In this case, theta equals 30 degrees, represents a straight line that goes through the pole. Okay, and in this case, the angle here is the angle that the line makes with the positive polar axis. And r equals a constant, represents a circle centered at the pole. Okay, now what about more complicated equations? Well, when you first had a more complicated equation in rectangular coordinates, when you didn't have anything better to do, you started by making a table of values. For example, if we wanted to sketch y equals 2x minus 3. Of course, we know now this is a straight line. We've had a lot of experience in the rectangular coordinate system. When we were first starting out, if you would remember, what we did is to make a table of values and to plot those points, and then we would get the graph of this equation. So, for example, you might let x equals 0. If x equals 0, y was -3. If x is equal to 1, y is 2 minus 3, or -1. If x is equal to 2, you get y equals 2 times 2, 4 minus 3, or 1. If x equals -1, -2, -3, -5. And you plot these points, 0, -3, 1, -1, 2, 1, -1, -5, and you connect the points. And of course, we get a straight line. We've had a lot of experience with equations in the rectangular coordinate system, and we know, of course, just by looking at it, that this is the equation of a straight line. But since we're just starting out in polar coordinates, we're going to have to start with the same kind of procedure of making a table of values. Of course, after a while, certain curves will seem familiar, and you will be able to recognize them by sight. Now, as our first example, let us graph the polar equation r equals 3 plus 3 cos theta. We need to make a table of values, various theta values, and figure out what their r values are, and then we'll plot the points r comma theta. Of course, this presupposes a knowledge of trigonometry. You at least need to know the cosine of the basic angles. Okay, let's see. Let's make our table this way so I can get some more in here. Let's say for theta we can consider 0 degrees. Let's go up from 0 to 360 by 30-degree increments. So 0 degrees, 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150 degrees, 180 degrees. Let's continue it over here. So let's see, 210, 240, 270, 300, 330, 360. And in each case, we want to know the R value. I'm going to put in an extra line in the table. I'm going to write down the cosine in each instance as an intermediate calculation, and then the R. Just to help us a little. So at least you'll know what you don't understand. We need, of course, the cosine of each of these angles if we intend to substitute in. So the cosine of 0 degrees is, of course, 1. The cosine of 30 degrees is the square root of 3 over 2, which is about 0.87. The cosine of 60 degrees is 1/2. The cosine of 90 degrees is 0. There is a videotape in trigonometry, okay, which explains how one gets trig functions of the basic angle. So if this is foreign to you, okay, you can finish this tape. But if you want to know where these angles came from, I would suggest you watch the review on trigonometry. Cosine of 120 degrees is -1/2. Cosine of 150 degrees is minus 0.87. The cosine of 180 degrees is -1. The cosine of 210 degrees is also minus 0.87. The cosine of 240 degrees is minus 0.5. The cosine of 270 degrees is 0. The cosine of 300 degrees is 0.5. And for 330, 0.87. And for 360 degrees, 1. Well, assuming you accept those values for the cosine function, then the rest is pretty simple. We're just going to substitute in these values for cosine theta, triple them, add 3, and figure out what R is. So, for example, at 0 degrees, cosine theta was 1. So 3 times 1 is 3 plus 3 gives me 6. 3 times 0.87 comes out 2.61. Add 3, 5.61, let's say 5.6. 3 times 0.5 is 1.5 plus 3, that's 4.5. At 90 degrees, the cosine of 90 degrees is 0, so 3 times 0 plus 3 is just 3. Now, 3 times the minus 0.5 is minus 1.5 plus 3 is 1.5. That was 3, take away 1.5. Tripling this, we get about minus 2.6. 3 take away 2.6 is 0.4. And here, minus 1, 3 times minus 1 minus 3 plus 3 gives us 0. Okay, over here, tripling this, minus 2.63 and minus 2.6.4. 3 take away 1.5, 1.5. 3 plus 0, that's 3. And then 3 and 1.5, 4.5. 2.6 and 3, 5.6, and then 6. Okay, so we have our points that we have to plot. Let's do this over here. Okay, a good way to start off would be, and we're not drawing the quadrants, but we have drawn the polar axis, which is the 0 degree ray, and its extension for 180 degrees. This is 0, 90, 180, 270. And let's see. 30 degrees and 60 degrees, 120 degrees and 150 degrees, and then just the extensions. 30 extended to give you 210, 60 extended to give you 240. And over here, 120 extended to give you 300, and 150 extended to give you 330. You could also draw concentric circles to indicate 1 unit, 2 units, and so on, to help you in plotting points. In fact, there is graph paper especially designed for this.